At the nanoscale, materials behave in ways that often defy our everyday intuition. When matter is confined to two dimensions, only one or a few atoms thick, it begins to display extraordinary mechanical, electrical, optical, and quantum properties. These materials, known as 2D materials, include nanomembranes and quantum wells, and they are among the most promising frontiers in nanotechnology and quantum engineering. But what makes a sheet of atoms so special? And how can we harness these ultra-thin platforms for real-world applications? Imagine slicing a bulk crystal so thin that it essentially becomes a flat sheet, like peeling a single layer off a graphite pencil tip. That's how graphene was discovered in 2004. One atom thick, yet stronger than steel, more conductive than copper, and almost transparent. Graphene opened the door to a whole family of 2D materials, including transition metal dichalcogenides, like MOS2, hexagonal boron nitride HBN. These materials, each just a few atoms thick, offer a toolbox of tunable properties, from semiconducting behavior to magnetism, from piezoelectricity to superconductivity. Nanomembranes are a particularly fascinating class of 2D materials. These are freestanding, ultra-thin films, often fabricated using strain engineering or exfoliation techniques. What's surprising is that even when they are just nanometers thick, nanomembranes can remain mechanically robust, flexible, and even elastic. You can bend them, fold them, or roll them into microtubes. In fact, rolled-up nanomembranes have been used to create man-made nanomachines like microjet engines and tiny propellers, capable of moving through liquids under chemical or magnetic control. Because of their high surface area to volume ratio, these membranes are also ideal for sensing applications, detecting single molecules or ions with high precision. Then there are quantum wells, which are slightly different in concept but equally powerful. A quantum well is formed when a thin layer of semiconductor is sandwiched between two layers of a material with a larger band gap. Electrons, or holes, get trapped in this thin layer, confined in the vertical direction but free to move in plane. What happens next is pure quantum mechanics. Particles behave like waves, and their energy becomes quantized. This energy quantization allows for precise control of electron behavior, which is critical in lasers, photodetectors, and high-speed transistors. Quantum wells are the basis of quantum cascade lasers, which are used in spectroscopy, environmental monitoring, and even medical diagnostics. Why is confinement such a game changer? When electrons are limited to two dimensions, they scatter less, exhibit higher mobility, and respond more strongly to external fields. The result is enhanced performance in field effect transistors, flexible electronics, and photovoltaic devices. For example, MOS2-based transistors can switch faster and operate at lower voltages than traditional silicon, making them strong candidates for post-CMOS electrons. When stacked layer by layer with atomic precision, sometimes called van der Waals heterostructures, 2D materials can form designer quantum systems with tailored properties. You could, for instance, combine graphene's conductivity with HBN's insulation and MOS2's semiconducting nature to create ultra-efficient tunneling devices. These structures are not only relevant for electronics. Because of their sensitivity and biocompatibility, nanomembranes are also being explored in biomedical applications, such as implantable sensors, drug delivery platforms, and even artificial tissues. Their ability to be shaped into 3D architectures, such as capsules or scaffolds, opens the door to biohybrid systems that combine living cells with engineered materials. Are there challenges? Of course. Fabricating high-quality, large APIA 2D materials remains difficult and costly. Interfaces between layers can suffer from defects, and stability under ambient conditions is still a concern for materials like phosphorine or silicene. Yet, rapid progress is being made, especially with chemical vapor deposition, CVD, and molecular beam epitaxy (MBE) techniques. Theoretical tools and AI-assisted material discovery are helping predict new 2D compounds with exotic properties, such as topological insulators, spintronic materials, and room temperature superconductors. So why does this matter? The emergence of 2D materials has launched a new era in condensed matter physics, quantum electronics, and nanotechnology. From building quantum computers to designing next-generation wearables, the ability to engineer matter in 2 dimensions is unlocking capabilities once confined to science fiction. Could a single sheet of atoms change the way we compute, heal, and power our world? For nanomembranes and quantum wells, the answer is no longer hypothetical, it's already happening. Fundamentals of 2D materials. Two-dimensional 2D materials are atomically thin sheets whose thickness spans only one or a few atomic layers, yielding extreme surface-to-volume ratios and unique quantum behaviors, as their reduced dimensionality confines electrons and phonons to a plane and dramatically alters electronic, optical, and mechanical properties compared to bulk counterparts. Nanomembranes and quantum wells exploit these effects to achieve high carrier mobilities, tunable band gaps, and exceptional mechanical flexibility for transformative applications in nanoelectronics, sensing, and energy devices, for example, graphene. A single layer of carbon atoms exhibits record-high electron mobility and tensile strength far exceeding steel, and this is analogous to a single sheet of paper compared to a thick book, where extreme thinness unlocks capabilities impossible in thicker forms. Atomic structure and mechanical strength. The planar honeycomb or layered crystal lattices of 2D materials provide strong in-plane covalent bonds and weak out-of-plane van der Waals interactions, resulting in high tensile strength and mechanical flexibility, with Young's moduli often exceeding terapascal values, which allows nanomembranes to remain ultra-strong and bendable without fracture while conformally coating irregular surfaces. For example, molybdenum disulfide nanomembranes maintain electronic function when wrapped around fibers as thin as a few micrometers, much like a steel foil, so thin it can fold like paper, yet remain unterrible under tension. Electronic band structure and quantum confinement. In quantum wells, charge carriers are confined in one dimension to a thin semiconductor layer sandwiched between wider gap materials, creating discrete energy levels and tunable band gaps that produce strong excitonic effects and enhanced optical absorption or emission at specific wavelengths, enabling precise engineering of electronic and optical properties for lasers, LEDs, and high electron mobility transistors. For example, GaAs/AlGaAs quantum wells emit bright narrowband light in diode lasers used for optical communications, analogous to shallow swimming pools that restrict swimmers' vertical movement and force them into discrete horizontal lanes. Thermal transport and heat management. 2D materials exhibit exceptionally high in-play thermal conductivity, as seen with graphene, which can exceed 2000 W/mK, while cross-plane conductivity remains low due to weak interlayer coupling, allowing efficient lateral heat spreading with vertical thermal insulation, ideal for hotspot management in microelectronics. For example, graphene heat spreaders integrated under microprocessors dramatically lower peak operating temperature, much like a carpet that quickly spreads heat sideways while preventing it from seeping down into the floor. Optical and photonic applications. Quantum confinement in 2D materials enhances light-matter interactions by producing strong absorption, photoluminescence, and nonlinear optical responses, with tunable bandgaps across the visible and infrared spectrum, enabling bespoke photodetectors, modulators, and lasers at atomic thickness, while nanomembranes' transparency and flexibility support foldable displays and conformal optical sensors. For example, most 2 photodetectors achieve high responsivity for visible light with sub-picosecond response times, analogous to a window that not only lets light pass, but can instantly change color and intensity on command. Chemical sensing and biosensing. The entire volume of a 2D nanomembrane is exposed to its environment, rendering its electronic properties extremely sensitive to surface adsorption of molecules, and when combined with quantum well heterostructures that amplify sensitivity via band structure shifts upon analyte binding, this enables ultra-sensitive detection of gases, biomolecules, and ions down to single molecule level, with flexible forms suitable for wearable diagnostics and environmental monitors, for example. Graphene-based sensors detect parts per billion concentrations of nitrogen dioxide with rapid response, much like a touchscreen that instantly registers the lightest fingerprint without requiring pressure. Energy conversion and storage. Layered nanomembranes offer high surface area and rapid charge transport for efficient electrodes in batteries and supercapacitors, while quantum wells engineered at interfaces improve charge separation in photovoltaic cells to boost conversion efficiency, and their mechanical flexibility supports bendable energy devices for portable and wearable power, with tunable band alignments also optimizing catalytic activity for hydrogen generation and CO2 reduction. For example, graphene oxide electrodes and supercapacitors deliver high capacitance and rapid charge-discharge cycles for grid-scale storage, analogous to a sponge with built-in wires that maximizes contact area while swiftly conducting electrons. Integration into flexible electronics. The atomically thin nature of 2D materials enables fully flexible transistors, sensors, and circuits that can bend, stretch, and fold without performance loss, while quantum wells embedded in flexible substrates produce high-speed logic devices for wearable computing and foldable displays. And layered heterostructures stack multiple functional 2D sheets into multifunctional flexible stacks that pave the way for next-generation human-machine interfaces and implantable electronics. For example, flexible MOS2 transistors maintain stable on/off ratios when bent to a radius of 2 millimeters, much like an origami sculpture. Complex functionality packaged into a foldable, lightweight sheet. Future directions and challenges. Scalable, defect-free synthesis and reliable transfer of large-area 2D nanomembranes remain key manufacturing hurdles, while quantum well devices require atomic-level interface control to ensure consistent confinement effects across wafer scales. And integrating 2D materials into existing semiconductor fabrication processes calls for new patterning and packaging techniques. Overcoming these challenges will unlock widespread deployment of 2D-based high-performance, flexible, and multifunctional technologies, as illustrated by roll-to-roll chemical vapor deposition of graphene, advancing toward industrial wafer-scale production, analogous to mastering a new culinary technique at restaurant scale, where recipes work in the lab but need robust processes for mass production.